And am I causing trouble by going across this line? I am. Okay. I'm going to have to learn some rules here. I think everybody who's had an undergraduate course of some sort knows what this course is about. It's about efficient algorithms. And efficiency either in terms of time or space, which means memory. But we want to be a little bit more precise about what all that means and what worst case means in particular, and what lower bound means and so on. And it's worth doing this at least once right. So then you can fall back on those strict definitions if you're ever confused. Then as soon as we do the formal definitions, as soon as we're finished with them, we almost never talk about them in those terms, and we go back to the hand-waving, worst case, big O kinds of things where we're a little casual about what all this means. But let's just start with some problem. So I'm going to let P denote some problem. That's sort of an abstract thing. And if you want to be concrete, so you have something clear and specific to think about, you might think about sorting numbers, for example. But it could be any problem. And given that problem, we have algorithms that solve that. Now, what do I mean by an algorithm? Well, in this game plan, we'll deviate from this to some extent, but for most of the game plan in this course, we're talking about deterministic algorithms, which means they do the same thing each time you feed them the same data. So that's deterministic. So an algorithm is deterministic. Okay. And when we run that algorithm, and we usually want it to be correct. There should be a very clear semantics of what it means to solve this problem, and therefore what it means for the algorithm to be correct. And one of the things we do in this class is to prove that algorithms are correct. And that's one of the things you have on your first homework. I've given you a problem, I've given you an algorithm, and your task, there are two of those types of questions, is to prove that the algorithm is in fact correct. Okay? So we're dealing with algorithms that are deterministic and that are always correct on all inputs, and we'll deviate from that later on in the class when we talk about randomized algorithms. But given that, then there is some universe. Well, I should say, we then have to deal with the size of input. Okay, if we're going to be giving input to the algorithm, we're going to be interested in how fast the algorithm runs as a function of the input size. So we have to have some notion of the size of the input. That's really a matter of modeling and what you think is appropriate. If you're given a list of numbers, for example, oftentimes we take the size to be the number of numbers. But if those numbers are extremely big or extremely small, it might be more appropriate to consider the number of bits that it takes to represent them. Or if the algorithm interacts with that list in some weird way, and that interaction changes somehow as that list changes in that weird way, then that weird way has got to be introduced somehow, included somehow in the notion of size. I mean, just to take a fanciful example, maybe that algorithm behaves very, very differently on even numbers than on odd numbers. And then if that was the case, then your size would want to distinguish between the number of even numbers you gave it and the number of odd numbers you gave it. I don't know any algorithm that behaves that way, at least for sorting, but just to make that idea concrete. So we have to, on each particular problem and for each particular algorithm that you think about, you have to decide what the appropriate notion of size is. And so in our sorting analogy, it could be the number of numbers, as long as the behavior of the algorithm was fairly reasonable for that range of numbers. Otherwise, you might want to consider, as I said, the number of bits it took to represent them and so on. And then I should have looked at these notes that I posted on the web just to make sure I have the notation exactly the same as in the notes. I wrote those notes, I think, about 15 years ago. And I've been using them forever. But let me just invent now a symbol for that may not be the same as what's actually literally on the notes that's on the web. This is the set of all input, all possible input to problem P of size n. So we have a notion of size, and I should probably put a P down here. So in the case of sorting, if our problem P is sorting and n, the size of the input is the number of numbers, what does this represent?
The set of all list of numbers that have 25 numbers.
The set of all pairs of 25 numbers.
Yes, the set of all sets of 25 numbers. Okay, we didn't introduce an ordering on the. So far I haven't said whether the input to this problem is a list, that is, the ordering matters, or it's just a set. Sometimes that matters. But the point is, this is an infinite set, and it consists of inputs of sets of themselves or lists, depending on how we specify the input, of 25 numbers. And so this thing is infinite. All right. Then we're actually getting somewhere now. TAI for I contained in IPN. Okay. This I is a particular input taken from this set. So again, in our analogy or in our concrete example where we're talking about sorting, if P is the sorting problem, then this is some particular list or set, depending on whether we're considering the input to be ordered or not. This is some particular, let's just say, set of size n, which is going to be fed. Well, that's what it is. It's a list or a set of size n. And then this notation is the number of primitive steps, and I'll talk about primitive in a minute, that algorithm A does when given input I, and it's for problem P. So when you give a particular input to a particular algorithm, and it's a deterministic algorithm, that algorithm does something. And it does the same thing every time you give it the same input. And therefore, we can learn things about what it does when it's given that input. And what we focus on here is the number of primitive steps or number of primitive operations that that algorithm does when given that particular input I. Now, primitive, what do I mean by that? Well, what we want to do is focus on those operations which really establish the overall and dominant behavior of that algorithm. If we're interested in time, and this is with respect to time, we're interested in those operations which are the most numerous or consume the most time. The rest of the stuff is bookkeeping, clutter, other operations whose number is proportional to the number of operations, number of primitive operations. And so we can disregard those when we examine the behavior of the algorithm. Now, what you decide to be primitive is a matter of modeling and is a matter of the algorithm. For example, in sorting, what's the typical primitive operation? A swapping might be, although that's fairly specific to specific algorithms. Not all sorting algorithms swap. Comparison is a much more common primitive when talking about sorting algorithms. Take two numbers at a time and you compare them to see if they're equal or if one's bigger than the other. So it's not always true that comparison is the appropriate primitive operation for sorting. But for most of these sorting algorithms that we're going to look at, that is. Now, there are other algorithms where comparison of the entire numbers is not the dominant operation. There are algorithms such as radix sort where you're looking at bits. And then you have to talk about the primitive operation as being a comparison of bits. There are other algorithms where you compare and you do also swap. And it turns out that the number of swaps is bigger than the number of comparisons. And when you're looking at such an algorithm, then your primitive operation should be the number of swaps. Does anybody know of an algorithm where that's the case? Bubble sort, I know, yeah, maybe. I'm not sure. I'm thinking of a different one. Well, there's an algorithm called insertion sort, okay, where the number of comparisons, if you have a list of n numbers, is never more than a number proportional to n log n, function proportional to n log n, if you implement it correctly. But you have to do some swaps or some movements. Actually, it's not literally swaps, but it is movements of the data in order to make space for the inserted number. So in that case, the number of movements actually can grow to be on the order of n squared in worst case. And n squared is a bigger, faster growing function than n log n. And so in that particular algorithm, the primitive operation, it wouldn't be appropriate to say that the primitive operation was comparison. The primitive operation would then be movements of numbers. Okay. So this is a part of the model that depends on the particular algorithm. All right, so we have a symbol here for the number of operations, primitive steps that algorithm A, that's a specific algorithm, does on a specific input. Purely deterministic, and shouldn't be any ambiguity about that. Now, this is the most important function we're going to study in class. WA is the max over I contained in capital I Pn of T AI. So what is this talking about?
The maximum runtime for all problems of a given time.
Right. This is a function, first of all. This is a function of n. Okay. And so here's n, here's WA n. And what we're saying is for any particular size n, let's say 25, we're thinking of all of the possible inputs of size 25 that could be given to algorithm A for solving problem P. And what's the maximum over all those possible inputs, the I contained in here? What's the maximum number of primitive operations that that algorithm takes? And then we plot that. And you plot it for, conceptually, of course. We're not going to ask you to do this. And this function here is WAN. And this function is just loosely referred to as the worst case running time or worst case behavior of algorithm A. And what's implicit when we just talk about, oh, it's the worst case running time, what's implicit is that we have, we've decided on what the primitive operations are, and we've decided on what the size means. And if those aren't ever stated explicitly, or you can't go back and figure out what they are for this particular function, then this isn't really well defined. But assuming that we know what those two decisions were, then this function is a well-defined object. We may not be able to figure out what this function is, and what this class, to a large extent, is about is what we can do to figure out this function for specific algorithms. We'll have other functions that we're interested in as well. But this is the principal thing that we'd like to get our hands on for specific algorithms. OK. Let me just fill in a little bit more of this picture here. There were other data points here. this is for different algorithms. Sorry, this is for different inputs of that size. This is still fixed on this algorithm. So on some inputs of size 25, that specific algorithm A did many fewer operations. So this is operations over here. And this is the function. So for some inputs of size 25, that algorithm did many fewer operations than the point that's on this curve. Okay? And it's a legitimate question to ask, why do we consider the high points here on this picture? Why don't we consider the low points or the middle points or some other kind of function of the entire data space? Anybody have an answer to that? Yeah.
Well, high points guarantee on operation or running time.
Yeah, that's one argument. One argument is that this is a guarantee. If we've learned this particular function, WAN, and it's based on this worst case viewpoint, then we're guaranteed that whatever data we get, if we know its size, we can predict that the running time for this algorithm will be less than or equal to whatever this function tells us. So it's a kind of a guarantee, and there are certainly instances where guarantees are important. Well, but the other reason, I'll tell you, the actual secret reason.
Easier to calculate.
It's more tractable, yes. We've been simply more successful in learning things about this function than other functions that some people might think are more relevant. I mean, you might think that, let's say, the median function or some kind of weighted average of these or some more average behavior of the picture would be more relevant and more interesting to know about. Generally, those other functions are technically more difficult to learn about. We've simply been much more successful in learning things about this function, the worst case running time function, than other functions. Maybe we could learn something about this one, the best case. And sometimes that's relevant. If the best case isn't particularly good, then that might be an interesting fact as well. But usually the reason you don't focus on the best case is it's just not interesting. It's just too unlikely that it's going to represent the data you'll see in practice. And therefore, there isn't a huge effort in learning things about the best case. OK, so this is worst case. Now, before I go on to the next function that's written up in the handout, let me talk about asymptotic notation. Because, and by the way, I won't do this in this class, but in the undergraduate class, one of my favorite exam questions, which I tell them ahead of time. I mean, I tell the undergraduate class, this will be on your exam, is to simply state in words what this notation just said. Okay, and only about half the class tends to be able to do that. But I won't do that for this course. But it is certainly something you should make sure that you can do, that you can look at that particular formulation and parse it and really say what it was stating there. All right, so we'd like to know this function for some specific algorithm that solves some specific problem. Generally, that's very hard to get our hands on, that function exactly. I mean, on some occasions, we're able to get it. But most of the time, we don't. So we have to try to approximate it in some way. And there are two approximations that people usually try for. One is from the top, and one's from the bottom. Okay, the upper bounds and lower bounds on this particular function. So an upper bound, ideally, you'd like to have some other function which is always greater than or equal to this function. So some upper bound on WA of n. And ideally, a lower bound should be below it everywhere. Okay. But that's quite difficult to obtain also. It's difficult, has traditionally been difficult to find functions that are always above or always below, and provably so. And of course, what you want are two approximations. You want approximations from above and from below, which are actually very close. You'd like to be able to say that the deviation from the upper bound to the function is small, and the deviation from the lower bound is small. And usually the way you can get that piece of information is by showing that the deviation between the upper bound and the lower bound is small. You don't know exactly where the function w is, but if you have an upper bound function and a lower bound function and they're not too far apart, then you know that you've bracketed the w fairly well. Okay, but we usually can't get our hands on such nicely behaved upper bounds. Instead, what you'd like to have, what is attainable more commonly, is some function which kind of misbehaves on small values of the input size. Sometimes it's above, sometimes it's below. It doesn't actually act as a very good upper bounder. But as n gets bigger, as the input size gets bigger, then it tends to be above maybe everywhere, or at least an infinite number of points as you increase n. So our upper bounds want to look like that, and similarly our lower bounds want to look like something like that also, which eventually get to lower bound the function that we're really interested in. Okay, so given the fact that it's unlikely we're going to get upper and lower bounds that are actually above or actually below everywhere, but are eventually above or below, eventually they do the right thing. And given the fact that we're only looking at primitive operations, we're only looking at a subset of the operations that the algorithm actually does. We're not going to count every second that's consumed or every operation that's consumed by that algorithm. We don't need to know these bounds or this function that precisely. We only need to know that, or try to know that, up to some level of precision. And hopefully everybody here knows where I'm going with this. Anybody would like to fill in the blank? What comes next?
O.
Go.
O.
Yeah, big O, omega, theta, little o, asymptotic notation. We're only dealing with asymptotic behavior. We're not dealing with exact behavior. There's a lot of wiggle room in the functions that we're going to talk about. And so we want some notation that deals with that fact. So asymptotic notation, and the most important one is big O. And so we say that a function f of n is big O of g of n. So one function is big O of another function. And let me write what this means roughly. If this is g of n, f of n is, I'm sorry, I just got it backwards. F of n is the function we care about, and that function is big O of g of n. It means that eventually and roughly, g tends to grow as quickly as f does. Yeah. Or more. So that f is bounded eventually by g of n. And let me just write that a little more precisely. I can say this is if f of n is big O of g of n, if in the limit, as n goes to infinity, g of n over f of n, well, what do I want for this? What are the possibilities?
Infinite.
Greater
than infinite. Greater
one
than,
possibility is infinite,
greater than 0.
or one possibility is that it's some finite number bigger than 0. Okay? So either this becomes a constant bigger than 0, or g really outstrips f. Okay? And then this is infinite. Okay? So let's just, as an example, if f of n is, say, 15 n squared, and g of n is 35n cubed. So you see that f of n is certainly big O of 35 of g of n. Okay? Now let me give you a little more interesting example. Suppose that f of n is the same, 15n squared, but g of n now is equal to n squared over 15. Then is f of n big O of g of n?
Yeah.
Yeah, it is. If you look at the limit here, okay, you get a constant, and what is the constant? 1. 1?
No.
15 squared.
1 over 15 squared.
It's what?
1 over 15.
Yeah, 1 over 15 squared. Okay, I believe. It's a small number. It's a small number less than 1. However, it's bigger than 0. And that's important. And the key point I'm trying to point out here is that f grows faster than g in this particular example. G is growing as n squared over 15, but f is growing as 15n squared. So f is growing faster. Nonetheless, we say that f is big O of g because these constants, the 15 here and the 1 over 15 here, this is small change. This is a constant which just is modifying the overall dominant behavior. The overall dominant behavior is here in the quadratic term. So you go back to this definition. Now, one thing you might notice is I've said this is if and not, I didn't say it was if and only if. And in the book, they may have a more complete definition, which will give you the other side as well. And just to give you a hint as to why this is not both necessary and sufficient, is just that sometimes this limit doesn't exist. Okay? But that's more mathematical than we need to be. This is an engineering course. We don't have to worry about those things too much. So this is basically going to be our operational definition to see when one function is big O of another function. Just take the limit of the ratio. Okay. Well, there are two other functions that are of importance. F of n is omega g of n. And this is when the limit of n goes to infinity of g of n over f of n. Well, what I want from this is to say that f of n, intuitively what I want from this is to say that f of n grows at least as fast as g of n. But again, in the technicalities of this, the constant factor here, and whatever small change was out here, I mean, in addition to this n squared, you might have had an n term or n log n term, something that grew slower than the n squared. Those things will fall out when we take the limit of the ratio. So if intuitively what I want is that f of n grows at least as fast as g of n, then what are the possibilities over here?
Either a constant or 0.
Yeah, if I want f of n to be growing at least as fast as g of n, maybe it really, really dominates g of n, in which case this thing goes to 0. Or it's about the same after all the constants get canceled and the small terms fall out. And then we have a constant which is bigger than 0, but we don't have infinity. Okay? We don't have the case that g of n really outstrips f of n, then this limit would be infinity. Now, can somebody tell me another way of writing this?
G of n is big O of f of n.
Yeah, this is if g of n, this is the sort of reciprocal relationship, is big O of f of n. Okay, and this is actually. So these two, the big O and omega, it's a matter of convenience which one you use, because we're really talking about a relationship between f and g that could be expressed either way. All right, and then the final notation is this that we're going to use. F of n is theta of g of n. Well, this is if and only if f of n is big O of g of n and f of n is omega of g of n. So if we have both of those things happening, that it basically grows no faster than g of n and basically grows at least as fast as g of n, then what is it growing as?
As G of n.
F of n and g of n are growing roughly at the same rate. And how do we write that in terms of limits? So this thing is, if the limit as n goes to infinity of that ratio equals what? Some constant greater than 0. Okay, so this was the intersection of the two possibilities that we had before. One possibility was infinity and a constant bigger than 0. The other one was 0 and a constant bigger than 0. And you throw out the two extreme cases and you get the intersection that happened. So these will be our principal three asymptotic notations. There's another asymptotic notation which is little o, and I'll let you look in the book if you're not already familiar with that. It's not used very much in this context. All right, so back to the W, the worst case running time that we're principally going to be concerned about as a function of n. Mostly, we're not going to be able to get our hands on this exactly, but we'll be able to get our hands on functions, some functions here, g of n, where we know that WAN is big O of g of n. That's the kind of thing we'll be able to prove. Or we'll have WA of n is omega of g of n. Sometimes we'll have such results. And sometimes we'll have both. And so we'll be able to say that WA of n is omega, is theta of g of n. Okay? So those are the kind of desirable results we'll want and will obtain about specific algorithms. All right, well, all of this was in terms of specific algorithms. Now I want to get into the next level of abstraction, which is about the complexity of a problem, independent of what specific algorithms we're talking about. So we have a problem, for example, sorting again, and we're talking about deterministic algorithms and correct algorithms, but we don't have anyone in mind. But we can just define the worst case behavior of problem P as a function of n. And that's going to be the min of WAN over A, an algorithm that solves. So in fact, I should have put a P here, problem P. This may be a little more abstract and a little bit weirder than most people are used to. But again, I have a picture where I have along here the input size, n. And along here, I would have WAP, n. We're talking about specific algorithms that solve problem P. And their behavior as a function of input size. So for each algorithm that you can think of, or each algorithm that exists, and this is again conceptual because there's an infinite number of algorithms. So for n equals 25, this is what WA n is, or for 25. Let's say for A being merge sort, if we're talking about sorting. And here's WA 25 for bubble sort. So we have all of these data points on this conceptual graph, and then connecting the lower dots that's what WP of n looks like. Now, who wants to interpret this one? Tell me what's this getting at? What does it mean?
Each input size is the best algorithm.
It's what?
It's the best algorithm for each input size.
Close. The answer was, the suggestion was it's the best algorithm for all inputs. The best algorithm for what?
For an input size at a point, at a certain
It could be
point.
different algorithm.
Be different algorithms, though.
It could be different, yeah. I'm talking about this curve, yeah, in the back.
Best possible result over any algorithm that you can choose.
Yeah, sort of. This is, first of all, a function. It's a function of n. And what it is, this is a lower bound function on any particular WAP n. I mean, that's actually that's just by definition. I haven't really said anything very interesting. If I look at this curve, this function, and I think of any other particular WAP, an algorithm for a curve for a specific algorithm, it's of course got to be up above for a specific A. Anybody? There was another hand up there, out there? Yeah.
Bottom one is just saying that given the problem P,
It's what?
bottom curve is saying that problem P for a particular solve no faster than this.
Yeah. This is saying that this function is a lower bound on WAP for any A. Now we're going to have to modify this a fair amount so that, because we've talked, when we defined WAP, we had to implicitly or explicitly talk about what the primitive operations were and what the size of the input was. Okay, and this curve has got to play the same game. It's got to be along the same rules. But this function is a lower bound on WAP n for any algorithm A that solves problem P. And the point of making this so formal is that sometimes we can actually come up with such functions. We can come up with a function WPN, which is a lower bound on WAPN for any A. And what it's getting at is the inherent complexity of solving problem P, at least within the confines of the worst case viewpoint. That's what the W is doing here. And within the confines of what we've decided as the primitive operations and what we've decided for the size of the input. But given that we fixed those two things, and we're interested in finding WAPs that that's n. We're interested in finding algorithms that push this curve down. And if we know this thing, we know a lower bound below which we cannot push any specific one of these curves. And moreover, if we have such a lower bound, and then we have in our hand a particular algorithm whose function is fairly close to this thing, then we're able to say that our algorithm is fairly good, and we can be more precise than that. If, in fact, if W APN is omega of WPN, then we declare A is optimal. Well, optimal with respect to all of the decisions we've made in the model. The model is worst case. It's with respect to what we've taken as our dominant operations or primitive operations, and with respect to what we're calling the size of the input. Okay? So we want to have these lower bounds on the inherent complexity of problem P so that we could then gauge how close to optimal is a specific algorithm A. Notion of inherent complexity.
You said omega?
Did I say, I meant theta. If I said omega, I'll review the tapes and see if I.
No.
I meant theta, definitely. Omega is by definition. Okay, this is definitely, WAPN is definitely going to be omega WPN for any A. But if it's theta, then we're in good shape. All right. That question threw my train of thought off. What was I going to get to the next point here? Anyway, for some problems, we'll be able to get these nice lower bounds. We'll be able to squeeze to see that there's an upper bound for some WAPN that's close. And so usually what happens is you get an upper bound on some WAPN, which is close to the lower bound on this WPN. And then you know that your algorithm, you can declare your algorithm to be optimal or close to optimal. Oh yeah, I was talking about the inherent complexity. The inherent complexity of a problem, as opposed to a specific algorithm, is sort of analogous in a way to a notion of work in physics. Say that, if I want to raise this eraser from this point on the table to this point in space, there are lots of ways I can do it. I can just go straight up, or I can take some curved trajectory, or I can put explosives there, or bring in a crane. There are lots of different ways of doing it with different expenditures of energy. But there is some inherent lower bound on some inherent amount of energy that needs to be expended in order to move it from here to here. And this function, WP, is really trying to get at that sort of notion in the world of computation. It's much more constrained because everything is relative to the model of computation that you set up. And sometimes it's an interesting thing that happens frequently when people come up with algorithms whose worst case running time, whose WAPN is lower than very well known WPN. Okay, I mean it happens frequently that there's a well-known function WPN, and everybody knows that you can't have an algorithm that beats that. And say a typical one is n log n. Okay. And then somebody comes along with an algorithm whose WAPN is smaller than this function. Okay, let's say n over 2. I don't know, just to make up some function. And the resolution is that they were playing different games. They had different models. This was proven with respect to some choice of what the primitive operations were, what size of the input was, what the permitted operations were, and so on. And this algorithm violated those assumptions. And then you learn, or the field learns, that maybe make the best choices in deriving this lower bound. When we were deriving this lower bound, people weren't thinking about certain operations. For example, it turns out that you can sort numbers by using arithmetic instead of numerical comparisons. I don't happen to know one of those algorithms off the top of my head, but there are some really weird algorithms which involve multiplication of numbers instead of comparison of numbers, which end up sorting the numbers. Okay? Well, multiplication wasn't in the model that proved this WPN, the primitive operations or the accepted operations that proved these lower bounds didn't include the possibility of multiplication or other division or other arithmetic. They were talking about comparison of numbers or movement of numbers, and not strange things like taking the square root of the number, which I think some of these algorithms do. All right, so that's enough, I think, for the rules of the game. So when we talk about the lower bound or the inherent complexity of a problem, we're talking about such a curve. When we're talking about upper bounds and lower bounds on the complexity of a particular algorithm, we're talking about such a curve. And generally, if you get the model right, this curve, this function, is above that function. And we almost never get either of these functions exactly. We always get them to within some accuracy described by big O or omega or theta notation.